This is a wave display. And the lower display is actually showing you the vibration of the air. And you notice it's kind of complicated. It's made worse by the fact that the scale is changing all the time. Let's see if I can change that. If I go to scale number 2, and the vertical scale, I don't want to auto scale. It was changing the vertical scale. So now let me change that to this. Now I'll whistle. You notice a whistle is sort of a very regular wave. It oscillates on and on and on. The air that's coming out of my lips just vibrates and keeps on vibrating. The upper scale shows you the frequencies, the number of cycles per second. You look at that. It has a funny scale there, but that's about 1,000. 1.1 K means 1.1 thousand vibrations per second. When I'm talking, notice how complicated it is? What that's showing is there are lots of frequencies present. But when I whistle, and you can see that on the bottom, there are high frequencies and low frequencies. It's a mess. If I whistle, it's nice. Basically, one frequency, one wave with a certain number of cycles per second, about 1,000. I can adjust the frequency and go down in frequency. I can't really go very low, down to 500. I'm not good at whistling at super low frequencies. I can sing. The wave gets kind of complicated. Because if I have two different whistles at the same time and they're different frequencies, you wind up getting something more interesting when I'm talking to you. My frequency is often high and low and middle and in between and all at the same time. Very complicated. Your brain is able to understand all this stuff. It's rather amazing. I think it's perhaps the most amazing thing about humans is their ability to be able to interpret this complex information instantly. So, well, you know, maybe you have to think a little bit about what I'm saying. But for the most part, you hear me saying things and you understand them. And even for the most part, I could put out this extremely complex waveform to you without having to really think about it a lot. There are some people who find this so overwhelming that they stutter. But the fact that I can speak mostly the time without stuttering is an amazing aspect of my brain. Funny shaped wave, isn't it? Let me turn this on to what's called a whistle. Let's see. See that frequency? Let me go up in frequency. You hear me talking, there's a lot of mess in there. So that's about 500. 500 vibrations per second. That's what's hitting your ear. That's about 1,000. Now here's something interesting. This is what's called an octave. Okay, this is the letter, let's see. Let me play the octave. So how many people do those notes sound like, even though they're different, they're really the same? Those are both called the letter D. Compare these with these. A lot of people say, oh, that's different. Yeah, that's the same. I mean, it's different, but the same. They're given the same name. Now listen to these. Which one is most similar to this? People say this one. That's called an octave. And musicians will use an octave as notes that go very well together. If you look on this, you can see there's the octave. Watch. So that's one frequency. There's the other. Play them both. Look in the upper screen. One is exactly twice the frequency of the other. That's true of every octave on this thing. It's fun. Every time you go 8 notes, it's a funny thing for doubling. Doubling is 8 notes, A, B, C, D, E, F, G, A. It's called an A again because it sounded right, sounded good. They go well together. But that's called an octave because it's 8 notes. And the scale of notes here is based on that. It's a funny name, oct. It has nothing to do with 8. But it turns out to be exactly a doubling of the frequency. There are other things called a fifth. Let me play a fifth. So 1, 2, 3, 4, 5. This is a fifth. People say a fifth sounds good too. Let's try a fourth. In music, the fifth is also considered a very harmonious interval. It's a fifth because it's 5 notes. You play those together. You play a chord, you often play these 2 notes together. If you play a sixth, the musician somehow knows that that is going to disturb you a little bit more than if you play a fifth. Now, this was well known to musicians before they knew exactly what was going on. I mean, the scientists knew what was going on. It turns out if you're a fifth, if you're playing a fifth, this is exactly 1.5 times the frequency. And when you have numbers that kind of match like that, then they sound good together. And if you pick something that's not something even like that, here's one. The composer knows this will have a different effect on you than will this. Now what I'm doing here is a seventh. What kind of effect is that going to have on you? This is the magic of composing. I don't know if we even have the right words to describe the effect it has on you. But if I do an octave, it'll sound like music. You should take Saul Perlmutter's course on the physics of music if you really want to get into this stuff. The composer knows how to make use of these different intervals to bring about a psychological, an emotional, a spiritual effect in you. He's manipulating you by taking these different intervals, and I don't understand that aspect of composing at all. I don't even understand why that music has this effect on me. Certainly the fact that some intervals are pleasant and others aren't. But this is all it is. It's just the frequency. And I could, you could play this frequency, and there it is. And I can see it's about 600 cycles per second. It's about 1,000. Young people can hear sounds up to about 15,000. Now, you don't sing this high. But if there are sounds that are super high, maybe I could do it if I just take my fingernails and scratch it on the blackboard. No, I won't do that. I couldn't stand it. But they get these higher frequencies. And when you hear frequencies, you hear them simultaneously. The fact that the different frequencies all travel at the same speed means that I don't sound that different when you're far away than when I'm close. If my high frequencies traveled faster or slower, then when you're far away, you would hear things occurring at the wrong time. You'd hear my high frequencies maybe after my low frequencies. But for sound, all frequencies travel at the same speed. That's not true for other kinds of waves. For water waves, the long water waves, you look in the ocean and you see these big waves coming and going. The big long waves they actually travel faster than the little waves, the ripples. The ripples will go like this. The big waves will come in at a high velocity, different frequencies. Now, what do I mean by a frequency? If we have a regular wave like this, then you could talk about the period. And that's the time between the crests. So your ear is sitting there, and the wave comes push, pull, push, pull, push, pull. In 1,000th of a second, it goes push, pull, and back on your eardrum. That's called the period. The frequency, if the period is, let's say, 1/1000th of a second, then the frequency, you get 1,000 of those a second. It's 1,000. So the frequency, you put this in an equation, the frequency is 1 over the period. Period, you usually say 1 over t for time. So call it the period time, and this is the frequency f. So if it's 1,000,000 times per second, you won't hear it. But each pulse will last 1/1,000,000th of a second. Now, as the wave is traveling, here we have a wave that's traveling. And you can see here are the two crests. There's a distance between them. That's called the wavelength. L. And that's the distance. So you measure it in meters or feet or inches or centimeters or anything you want. And that's the distance. Now, you don't have to have a regular wave. You could have this, one pulse. What's the wavelength of that pulse? Well, it doesn't really have a wavelength. Wavelength is really described only for a very nice continuous pulse, like the whistle. It's the distance between repetitions. Now, it turns out mathematically, if you take a long wavelength and a short wavelength and a whole bunch of different wavelengths and all mix them together, you can get something that looks like a pulse. We'll talk more about that when we get to quantum mechanics. In that case, we say we have a wave packet. And a wave packet doesn't really, it has a size. And that's about the closest thing we get to a wavelength in it. But wave packets are important because many waves that we'll come across actually come in wave packets. A flash of light. It vibrates, but it comes in a bunch. It's a wave packet. A wave packet looks like this. Or maybe it just looks like this. But those are wave packets. They're still waves. The material isn't moving. This thing moves up and down, but in the wave packet, the thing that moves is the energy. That's the characteristic of waves. The substance that's waving really only moves locally, but the wave moves globally. What it does is it carries the energy. A wave is a way of carrying energy from one place to another. Also carries information. Suppose I want to say, turn on the TV when you get the wave. I sit here and now the good program's coming on. Turn on the TV. The wave comes down here through the electric wires. You pick it up. It rings. You turn on the TV. It's a way of sending information. You can send complex information. If I want to send the letter, suppose I want to send a letter of the alphabet. What I'm going to do is send you a number, 1 through 26. If I send the number 1, you'll think it's an A. 26, you'll know it's a Z. How do I send the numbers 1 through 26? Well, I could send 26 pulses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you can count them when they come. That's not a very efficient way of doing it. It makes much better to send a pattern of pulses. Let's say 001 will be the letter A. This isn't the way it's actually done, but this could be the letter A. 010 can be the letter B. 011 could be the letter C, and so on. And I make different patterns. So I only send 3 bits. This is called a bit. And the wave is either on or off. It could be magnet up or magnet down. This is how all information is sent in computers, by patterns like that, representing letters. Those letters could represent notes on the piano. They could be the brightness of a picture. I could send a picture by dividing up the picture into little pixels. And on each pixel, I'll indicate a brightness. And the brightness could be whether it's 1, B, C, D, and make it bright. And then you put together the whole picture, and you send these bits, and you send a picture by sending little ones and zeros. This is what's called binary. It's the way information is sent on the computer. And with a wave, you can send information or you can send energy. Those are the 2 main uses of waves. This is a wave packet. Wave packets confuse you because you don't realize a wave isn't an object. It sure looks like an object when I send a wave like this and it bounces. It looks like an object that's bouncing. It's a wave packet, a little localized wave. When I send an electron to you, I'm actually sending a wave packet. That's why it looks like a thing, because all the energy is in a little bundle. There's no energy here or here. The energy is in a little bundle. We learn from relativity, energy is mass. So it looks like there's a little bit of mass that's traveling, but actually it's just a wave. Here it's the wires that are waving. For sound, it's the air that's waving. For electrons, what's waving? Oh, the vacuum is waving, or the ether. Some people call it the ether. You'll find all sorts of books that said the ether doesn't exist. And what they mean by that is that ether isn't a thing. It's not matter. Matter is waving ether. But what is ether? Well, it's the thing which, when waves, gives us matter. Since we are matter things, it's like the ocean waves trying to discuss what is waving. They don't know about water. Well, for us, we call it the vacuum, we call it the ether. The thing which, when it waves, makes for a wave. Waves move from one place to another because one shaking object causes the next one to shake, causes the next one. I don't know how many of you have been, in a football stadium when people do the wave. Let's try that. What I want you to do is, I want this person here to wait until I raise my hand, and then I want him to raise his hand. So don't do it now. I'm going to go like this. When you see me do that, I want you to do the same thing. Everybody else, ignore everybody but your neighbor. The nearest neighbor, whoever that is. When you see your nearest neighbor do it, then you do it. Okay? Ready? You didn't do it? Ooh, wait, whoa. Who's your nearest neighbor? Who's your nearest neighbor? Okay, if you see, obviously this was a failure on my part. Let's say, as soon as you see someone within 10 feet of you do it. How's that? Okay, we'll try it again. He's not easily fooled. Okay, so the wave traveled up that way. This isn't quite a wave because I wasn't transferring any energy to him. He had stored energy. This was more like an explosion. Sometimes it's called a deflagration wave. Here I am, I'm full of energy, and I release some of my energy. That causes him to release energy. This is what happens in an explosion. And then the explosion moves as each one of you releases energy. In a wave, I would punch him in I would knock him over. It would be like a dominoes or something. I would actually transfer the energy over. Now what I'd like to do is the following experiment. I would like those of you near the top to be really fast. That is, as soon as you see it, you do it right away. Those of you near the bottom, I'd like you to be a little bit slower. Or not slower like that. What I mean is, when you see someone do it, you go, oh, okay, and then do it. So let's see if we can do this. I don't want you to be too slow. Because what I want to see, what I'm hoping to see, if this works, is that the wave will move very fast to the fast people. It'll be slow over here, and as a result, the wave will actually turn around and come back down in this corner. I don't know if this will work, but okay, because I'm not, you're not precisely timed. The thing is, if the people over here are slower, then the wave will get over to here in about the same time it took the wave to go all the way around like that. So this is the idea of why waves turn. Okay, so let's see if this works. Ready? There it is, ending up right down there. That actually worked rather well. Okay, let's do that again. I don't know if you were trying because you knew what I wanted, but I thought it kind of demonstrates the principle, because you see, waves happen when you trigger the neighbor to move, and you trigger their neighbor to move, and then if there are a whole bunch of people doing it and these people get slow, the wave winds up going in towards the slow side, one of the answers to the quiz. So let's do it again. Just everybody, I think it sort of works. So that's the principle behind waves. You affect your neighbor. There's a way that this can be drawn. I put it in an optional section of the text, but let me draw that. Oh, look at that. Who's back there? Secret room. Okay. You're in an airplane, and get a window seat, especially if you're going out over the ocean. Watch the waves. And here's the crest of a wave coming in to the beach. Now this wave, this little wave here, it's shaking, makes everything else around it shake. So you say it generates a wave in a circle like that. And if this was the only thing that's shaking, if you're there in the water and bouncing up and down, you will make circular waves going out. And this little water here also makes circular waves going out. Now the circular wave will have a crest, and it will have a trough. And then maybe another crest. Notice the trough here hits that crest. Now what happens if a wave is going up at one point and down at another, and they meet each other? They cancel. This one is saying, move up. This one's saying, move down. You wind up not moving. So when you have a lot of waves like this, all being emitted by this wave, by this shaking, you wind up getting cancellation in here, and they add up on this. So this wave creates this wave, creates this wave. And in fact, what you see is the wave moving. Now, if on the bottom it slows down a bit, so this one makes a slow wave, and this one makes a fast wave, and this one makes an in-between wave, then you wind up getting things like this, and the wave crest becomes this wave crest, and it's moving in a more downward direction. So waves turn towards the slower side. And you'll see that because so if you get into a beach where the water is shallow, the waves slow down. And when they slow down, so what happens is if you have a wave coming in, suppose the waves are coming in from a distant storm, and here you are in the airplane, you're seeing the waves come in, and then here's the beach. This part is shallow, and this part is deep. And so this part slows down. So the waves tend to turn towards the beach, like that. And you'll see that from the airplane. You'll see them as they're coming in from the distant, they turn towards the beach as this side slows down. Same thing happens with earthquake waves. They will turn. But one of the more remarkable aspects, well, let me talk a little bit more about tsunamis, because they were certainly in the news just a year and a half ago. And a tsunami is a water wave, but a very special kind of water wave. It's very tall and has very long wavelengths. Now, I have some of the numbers here for tsunamis. Just wanted to give an example. A tsunami comes about usually when there is an earthquake underwater. So what may happen is you have the land underneath the ocean, and then there's a sudden shaking. Now what that shaking does, it could be a fault, so the land suddenly goes boom like that. But deep under the ocean, let's say there's a fault and the water suddenly goes like this. Here on the surface of the ocean, the water gets pushed up suddenly. This creates a wave. The wave actually goes in both directions. It spreads out from the tsunami. Here we have the land. Now, the depth of this could be several kilometers. And typically, you will get a wave packet with a wavelength of several kilometers. So here you have, as you're coming into the shallow here you have this wave. And let's say this distance here is 10 kilometers. It's a very unusual wave. The height of the wave will tend to increase as the water gets shallow. That's because you have a certain amount of energy. And that energy is spread out over a lot of the depth. But when that energy gets concentrated into a smaller depth, the wave gets bigger. So out in the open ocean, the tsunami may only be 1 meter high. Now, it's 1 meter high. How fast does it go? I give a nice equation in the text, which you don't have to learn. But I want you to know roughly how fast it goes. And the equation that I give is that the velocity for these kind of waves is equal to the square root of the wavelength. Measure this in meters, and this will be in meters per second. Really simple formula. So let's put in 10 kilometers. So this is the square root of 10 kilometers, 1,000. Okay, and I'm sorry. This is not the wavelength. This is meant to be the depth. Okay. Now, if this is 10 kilometers, that's 10,000 meters. This is about 100 meters per second. Did I do that right? For some reason, I did it wrong over here. 100 meters per second. It's not quite as fast as sound. Oh, here's what I did wrong. Okay, I wrote there. Okay, forget what I just said for the last 2 minutes. Okay, I was getting this confused. There are two equations. One is for deep water waves. Deep. In that case, the equation is just what I said, that the velocity is the square root of the wavelength. If the water is shallow, and for a tsunami, even 100 feet is shallow because the wavelength is so long, then the velocity is the square root of the, it's about 31 times the square root of the depth. So take out in the open ocean where the depth may be 10 kilometers, which is 10,000 feet, and plug that into here, and you get that the velocity is about 3,100 meters per second, which is approximately the speed of sound. So you have this super fast wave. And it may be only a meter in size, but it's going at the speed of sound. Now imagine you're in an airplane and here's this little wave, and it's going at the speed of sound, really fast, on the ground. But now think about this wave. You have a wave that looks like this. It may be a meter high, but this distance here is 10 kilometers. So when you're at the top of the wave, how long does it take for the next wave to reach you? It's traveling at the speed of sound, 300 meters per second, 3,000 meters per second. This is 10,000 meters. I'm sorry, this is, sorry about that, 300 meters per second speed of sound. I should look at my notes more. Square root of 10,000 is, V here is 3 times the square root of that. That's about 300 meters per second, which is what I said, the speed of sound. This is 3.1. That's correct. Thank you, Zach. Okay, look at the blackboard. 3.1 times the square root of the depth. It goes about the speed of sound. Here's what I'd like you to remember. Remember that in the open ocean, the tsunami moves at about the speed of sound. which is about 300 meters per second. You may remember it as 1 mile every 5 seconds. That's pretty fast. That's how fast it's going. It may be a meter high. How long does it take it to go at the speed of sound? 10 kilometers? Well, in 3 seconds, it'll go 1 kilometer. To go 10 kilometers will take 30 seconds. So this thing is moving really fast. From here to here, maybe 15 seconds. So here you are on the ocean, and this wave is going to come by. And the wave is a meter high, like three feet high. And here comes the wave. And it takes 15 seconds to get up a meter. And then 15 seconds to go back down. Doesn't seem like much of a wave. The wave is moving fast, but the water is rising slowly because the wavelength is so long. Picture this. Draw a little diagram in your notes. There's a contradiction here. You think this wave is moving really fast. Yes, but the wave is not just one little object. It's spread out over a long distance. When this wave gets to the shore, what's going to happen? Its amplitude will grow. It will get bigger. It may be 10 meters instead of 1 meter. That's 30 feet. So you have this 30-foot wave coming in. On the other hand, it's a gradual wave. It's spread out over 5 or 10 kilometers. So this huge wave is coming in, but it has a very gradual slope. It's like climbing a mountain. The mountain can go straight up, or it could be a very gradual rise. So imagine this water is coming in, but it's a very gradual rise. The result is the following. When you are on the shore, and this is worth knowing, I may save your life with this one, in comes a tsunami. And what is it like? Is it a wall of water? It's always described that way. I think it's described that way because that's what previous people described it at. Not because that's what people see. If you look at the movies of the tsunamis, what typically happens is the water begins to come in. It's rising. It may take 30 seconds to rise 30 meters. That means 1 meter per second. That's pretty fast. That means the water is going up like this. If you're on the beach and the water starts coming up that fast, and you're healthy and strong, get off the beach. You can outrun the tsunami. Because it will take 30 seconds for the water to reach its full height. Now, when that water's coming in, if it's very shallow as the water rushes in, you may get some broken waves right in the beginning. As this water rushes in, the sloshing will cause a few feet wall of water coming in. But you really have a lot of time because the wavelength is so long. So this is a very gradual wave, but it's a very big wave. And if you look at the movies, I have some of these somewhere. I could show them to you, of the tsunami that took place in Southeast Asia. You see the people there. This water's coming in, and then it keeps on coming. And someone watches, they see a wave on top of the water and say, oh, that wasn't so bad. But then the water keeps on coming and keeps on coming. And finally, it rises up and goes into the city. These things used to be called tidal waves. And the reason they were called tidal waves is they look like the tide is coming in. There's one case in Indonesia where, when the first wave comes, when the motion starts, it could be moving up or it could be moving down. It could be an increasing wave or a decreasing wave. About half the time it's a decreasing wave. And so here you are on the beach, and the water starts moving out. And what happens when water moves out? Suddenly there's these fish left behind, these beautiful shells down there on the beach, and so on. Wow, and people go down to go see this stuff. And at least on one beach in Indonesia, there was apparently a 10-year-old girl who said, Mommy, Daddy, this is a tsunami. We learned about this last month in class. And so the mommy and the daddy went out and warned everybody on the beach, get off the beach, a big wave is coming in. I estimated she saved several dozen lives by knowing a little bit. Because you can get out of the way. Because when it starts coming in, if it's a very shallow beach and you're rising 1 meter a second, that can go, maybe you can't outrun that. But if it's a steep beach, you get out of there. The real problem with a tsunami, it's the same thing as the problem with a hurricane. It's not that these big waves batter you. It's that you're underwater. You know, when the tsunami comes in, instead of being in the air, you're in the water. And being underwater is not a good thing for buildings or people. And with the water moving, with all the debris in it and so on, it's very easy to be killed. But that's what's going on with a tsunami. Earthquakes also travel fast. There are 3 different kinds of earthquake waves. And this is simply, there are different kinds of water waves too. There's the sound wave underneath the water. And then there's the surface wave on the top of the water. And those are different. The sound wave comes from the compression of the water. The surface wave comes because the water is moving up against gravity. And so remember on the surface wave for the water, if you're swimming there, you move in a circle, it turns out. That's the wave that moves on the surface. But in the volume of the water, in the bulk of the water, the vibrational wave comes about from compression. Rock is even more complicated. And so typically in the rock, you have an earthquake here, and 3 different kinds of waves come out of this. The first kind of wave is just the compressional wave. That is a backwards and forward shake. It's like the slinky wave, back and forth. That comes up. That usually arrives first. So here's the compressional wave hitting you. That's called the P wave. Stands for primary. You could also think of it as a mnemonic, that it's pressure. It's like a sound wave. And that travels pretty fast. If we're lucky, in the next half hour, we'll feel an earthquake. And if I'm really sharp, I'll sense that pressure wave. And then I'll start counting seconds. Because the second wave that arrives comes not from a compression, but from shear. What is shear? Shear is sideways motion, like this. Sideways motion can still send energy. Even though the motion is this way, the energy goes that way. Sometimes that's called a transverse wave. And if there's a break here, there may be a pressure wave that comes, but there can also be the side wave. So the pressure wave is moving forward and backward. That's the P wave. The second wave, the secondary wave, moves sideways. And sometimes, or the shear wave. It's called the S wave. It goes slower. So the P wave may go between 3 and 4 miles per second. This one only goes about 2.2 miles per second. So these 2 waves come out. This one goes faster than the other one. This one gets way ahead. The further away you are, the sooner it arrives. I mean, sooner than the second one. So if you're standing here and you feel the P wave, oh, P wave, ha. And then you wait. Is there going to be another one? Oh, yeah, there it is. The S wave. Sometimes, if you're really sensitive, you can tell the direction because the S wave is side to side. So if I move this way, then the wave must be coming from either that direction or that direction. Because it's the shear wave. Whereas the pressure wave, I move forward and back. They take different times, and that's just because rock is stiffer if you try to compress it than if you just try to bend it. And so because it's stiffer that way, this wave travels faster. If you have a stiff spring, the wave travels faster. So these travel at different velocities. They're generated at the same time. As they move, they separate. And so if you know the time between them, you can tell how far away it was. This is what they do with the earthquake records. They look at the P wave. They look at the S wave. From the time between them, it may be 10 seconds between the two. You'll see a squiggle in the seismograph. Looks like this. Right, there it is. And there's the secondary wave. And you get the time between them, and this is 10 seconds, then you know it's about 50 miles. 5 miles for every second away. That's where the earthquake came from. Now there's a third wave, which is actually, in some ways, the most interesting wave. The waves not only come to you directly, but they also tend to, they're going in all directions. The ones that come to the surface make the surface move up and down. And when the surface moves up and down like that, it gets a wave just like a water wave on the surface. Okay, so this is the surface wave. It's called the L wave. L wave may be because it's the last to arrive, but often it's the most destructive wave. It travels slower, about 2 miles per second. It moves only on the surface. Do you see why it's the most destructive wave? If you're far away, these waves are spreading out. They're spreading out in 3 dimensions. They're spreading their energy out over an entire sphere. Whereas this wave, when it gets to the top, is only spreading out on the surface. It's like the sound channel. It spreads out this way, but not up and down. It stays on the surface like a surface wave, like a water wave. So it doesn't spread out. So if you get really far away from the epicenter, then the P wave and the S wave may be really spread out. You can pick them up with a seismometer. But this surface wave that's coming along the surface, moving things, it's like a water wave. It's not a circle, but it's moving in an ellipse. It moves things around like that. And that can often do the most destruction. Now, just like with water waves, if these waves, if they get into a region where the wave is compressed into this L wave here, is spread out over a certain volume of rock. If you get into an area where the rock is not as stiff, where it's sort of softer, what happens to the L wave? Think about it for a moment. You're going from really hard rock, where this wave is moving along, to something now that's soft rock or sand or landfill. What happens is the energy still goes there, but now the wave will slow down a little bit. Now here's the paradox. Think about this. Wave is slowing down. That sounds good, right? So here we have this wave zooming along, and it gets into this region where it slows down. The front of the pulse hits it, then it goes slowly. The back of the pulse gets there, and it goes slowly. The wave is more compressed. When the wave slows down, the energy is in a smaller region. Just look at that. Here I'm coming. If I'm going really fast, and then my left hand slows down, and then the right one slows down. I didn't do that very well. They're coming really fast, and when it gets to this point, the first one's going to slow down. So now they're both going fast. Now only the second one's going fast. Now neither's going fast. So this is the paradox. You get into rock where the earthquake travels more slowly. You have the same energy, but now it's in a smaller volume. That means more shaking. So when the earthquake slows down, the earthquake wave slows down, you get more shaking. Where does this happen? Well, typically, rock, it travels really fast. Turns out, if you want to be on rock if there's an earthquake, the wave gets past you very quickly. The energy is spread out. If you get into what's called landfill, landfill is something I didn't know about when I was a kid, but people have all this construction, and then there's the water. And they run out of land. So what do? They take dirt and they fill in the land. You go over to San Francisco, go to a place called Water Street, and there's this blue line in the middle of the street. And over there, about 10 blocks away, is the water. The rest was all filled in. People wanted more land in San Francisco and Berkeley. If you look at a map of Berkeley and look at the freeway, here's the Bay Bridge. And then the freeway used to go this way and it used to go that way. And the bay is over here. So here's the bay. And here's the freeway. And this is where the freeway collapsed. If you look at a map of where the landfill was, the answer is that basically this is all landfill. It collapsed where there's landfill. The buildings in San Francisco that were damaged the most were the ones up in the Marina District on land that didn't used to be there. It was all landfill. You get the big amplitude there because the wave slows down. If you're in an earthquake in Berkeley, you want to be up on the rocks, not down in the soft rock we're right on the edge right now. We're almost right on the Hayward Fault. But when the earthquake slows down, it causes more shaking. Another thing that happens is the earthquake tends to have some very peculiar things. Waves are different from particles, from things, in the important fact that a wave that's going up and a wave that's going down can actually cancel each other. So if I have a slinky and the wave is going up, and on this side the wave is going down, when they come to the middle, the thing in the middle won't know whether to go up or down. In fact, it won't move at all. Energy can pass right through without this thing moving. It'll feel a stress. It'll feel a stretching, but it won't actually move. This is true of waves, of water waves. If we have two water waves, this is supposed to represent water waves or sound waves. And we have two emitters coming out like this. And here are these waves. And if they both reach you at the same time, this up wave and this up wave will make it move up even more. And this down wave and this down wave will make it move down even more. But if they arrive at different times, like if you happen to be in this direction and this is emitting waves and this is emitting waves, let's say it's sound waves, then this one goes up when this one goes down, they will cancel. Here I have an example of two tuning forks. And where's the little hammer I'm supposed to hit these with? Here it is. A tuning fork this one is designed to vibrate. It's precisely made, carefully machined, so it will vibrate at 256 cycles per second. We call that 256 hertz. This was because cycles per second didn't honor any grand old scientists. So we decided that 1 cycle per second is going to be called 1 hertz, or 1 Hz. So these days, people refer to frequencies in hertz. And this one is 256 hertz. Anybody have perfect pitch? What note is that? Someone said C. That's correct. Of course, you may know that tuning forks are usually set for C, and that's cheating. This one is also set for C, but we put little weights on it. And because there are little weights on it, it doesn't vibrate so fast. It has to pull those weights back and forth, and it slows down. I can take these weights off. Let me do that and see if they vibrate the same. So listen. That's the same note? To some people, they could really tell. I'm not very good at this. Let me do them both together. It's hard to tell there are two there. Really sounds like the same note. Now let me put the weights on this one to slow this one down. If I do this just right, this will vibrate slower. Now, the vibration from this will reach you. And maybe the vibration from this will reach you at the same time. And if they reach you at the same time, they'll both be pushing together. Your eardrum will be pushed in. You'll hear a louder sound because of the fact that there are two of them. And then this one, they'll vibrate back and forward, but this one's a little bit slower. So this one's going faster. And after a while, one of them will be pushing when the other one's pulling. In that case, your eardrum won't get any force at all. They will cancel. But then, because this one is really slow, not really slow, just a little bit slow, eventually, they'll get back in phase with each other. This one will slow down so much that it will, here's a diagram. Let me find a place where I can do a diagram. Here's the fast one. And then here's the slow one. And it starts out in phase, but it's slower. So after a while, it's going up when this one's going down. But it keeps on going slower and slower. And finally, once again, they're going up together. So as a result, here your eardrums will hear it loud. Here you'll hear it very quiet. Because they get in phase, we say, and out of phase. So if I do these together, what you should hear is that the signal will get louder and then quieter, and then louder and then get quieter. What you're really hearing is a constant signal from this one and a constant signal from this, but sometimes they happen to be in phase, they add, sometimes they're out of phase and they cancel. So let's see if you hear this loud, soft, loud, soft, loud, soft. Let's see. Whoa, 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 whoa. I turn one off, the beats go away, and you hear the constant tone. We'll try. It's really a constant tone. This one's also constant tone. Right now, because of where the mass is, this was slowed down a lot. And so they get in phase and out of phase quite a bit. In fact, if they have a difference in frequency, if this is frequency F1, this is frequency F2, let's say this is 256 and this is 266. If you want to know the beat frequency, it's just the difference between them. 10 cycles per second, 10 hertz. Piano tuners will use this in order to adjust a piano. They'll bring in their tuning fork, and then they will adjust this one until they don't hear beats anymore. Then they know it's in tune. If I put this way down here, it'll have less of an effect. If it has less of an effect, the frequency difference will be smaller. So they'll be closer in frequency. If they're closer, if this is, let's say, 256 and this is 257, then the beats will be 1 cycle per second. So if I try to match them, the beats will be slow. Let's see how that works. It's so slow that it's even hard to sense. Let me make it a little bit faster. Those are the beats. We can even make beats at different locations in space. So, for example, if I did this, suppose I have 2 speakers. The sound from the speaker spreads out in all directions. The one that's going to hit you is the one that's coming out in this direction, and from this one, the one that's coming out in this direction. And for you, maybe they cancel. Whereas over here, they'll reinforce. And then over there, they'll reinforce again. You see the pattern? Because here, this one is going further. They may be the same frequency, but it's going further. So with this one, that's where they reinforce, they come in together. But over here, it's up when this is down. So in this direction, they'll cancel. If we do this just right, if I had 2 speakers here, I could have the 2 speakers, and I'd say, for which of you is it loud? And we should get a pattern. A bunch of people here say it's loud, the people say it's soft, loud, soft, things like that. So that would be a good, hey, I have 2 speakers. Look at this. Okay, 2 speakers, the people right in front, it should be loud. Off that direction, this one's going a little bit further. If it goes exactly 1/2 a wavelength, then they'll cancel. So let's see if we can see this effect. Now, of course, you don't know whether it's loud or soft because you don't know how to compare it. So what I'm going to do is turn this. I don't want you to hear it through my microphone because I want you to hear it directly from the speaker. So I want to put the microphone down. And then what I'm going to do is slowly turn this. And as I turn it, you should go from the maximum sound to the minimum sound to the maximum sound. I want you to raise your hands when you hear the loudest sound. Let me turn this microphone off. Raise your hands when it gets louder. Now here's something else I'm going to try. I've never done this before, but we were talking about it yesterday, and I think it might be a fun thing to do. Some of you are now at the maximum, some of you are at the minimum. What I suggest you do is get out of your seat and walk. Maybe everybody should walk this way. And just get up out of your seat and see if you can go from a maximum to a minimum. And then you can go back. Once you get to a maximum or minimum, go back.
Are they
I don't know. Actually, Zach, I could switch the phase. I could switch the phase. I'll do that in a moment. Okay, try going back to your seats now. Don't use this as an opportunity. I see some people leaving back there. I know who you are. Okay, what I'm going to do another experiment, which is the following. This is Zach suggested this. What I could do is turn one of these upside down. And if I turn it upside down, where they are now a maximum, I turn one upside down, they'll now be a minimum. And so the pattern should shift. And there are some switches here, so I think I could do that. So let me try that. So this is called cancellation. And you see this in earthquakes. So I'm going to switch one now. For me, the effect is right back here is very dramatic, getting from loud to soft. If you happen to be right in the in-between region, you wouldn't hear any difference. Cancellation is important for several reasons. The cancellation, it's going to turn out, will be a major limitation of our spy satellites, as you'll see, because we use light, and light are waves. And this cancellation of light is going to limit what you can see from space on the ground. We'll be talking about that next week when we come to it. The cancellation is really important. When you have cancellation, you know you have a wave. This is ultimately how we know that atoms are made out of waves. Because you can take these atoms and you can cause them to cancel each other. It's an odd thing about cancellation because you think, hey, if they're canceling, what happens to the energy? The sound is coming out of here, and for some people, there's no sound. Where is the energy going? On the other hand, for everybody who's along the direction where it adds up, there's someone, or where it cancels, there's someone in a direction where it adds up. And so it turns out that this process is actually not eliminating energy. What it's tending to do is to focus the energy. So the energy tends to be concentrated among these bands and absent in the other bands. This turns out to be very important in radar. I have a pair, I didn't bring them in today, of noise-canceling earphones that I sometimes wear on the airplane. What the noise-canceling earphones do, they're very clever things. They go over your ear, and there's a little microphone on the outside. The purpose of the microphone is to hear the sound that's coming to my ear. Then what it does is it has a little circuit that takes that sound and broadcasts it into my earphone. Now this would normally make the noise twice as loud. But instead what they do is they turn it upside down. And so the sound winds up inside being canceled. So here I am with my very quiet earphones on. The airplane sound has just gone away. I turn the switch off, and then it's roaring, noisy again. Turn the switch on, and it's canceled. Where did that noise go? Well, it turns out that the speaker that is canceling it is making a wave that cancels it inside. But the wave that bounces off the outside is actually made stronger by that same speaker. What's really happening is the energy, instead of getting into my ear, is just bouncing off my ear. This is how the noise-canceling earphones work. In earthquakes, there are this phenomenon here, where there are directions where it's very strong and other directions where it's weak. In earthquakes, this can happen. For example, here's the epicenter. Now, the earthquake will go different speeds at different directions. There may be some region in here that reflects the earthquake. You may wind up getting an earthquake hit from two different directions. If you're unlucky, they will reinforce each other. If you are lucky, they will exactly cancel. And you can get this pattern of cancellations. This was seen in the Loma Prieta earthquake, where there's one building in downtown Oakland, which is, I remember, it's a big building shaped like the letter U. Okay? And one side of the building was destroyed, and the other side was basically untouched. That's probably an effect of cancellation. The fact that there are these directions in which the earthquakes add up, and then there are other directions in which they get weak. So again, this is a characteristic of a wave, and it's one of the ways people think of the earthquake as the ground shaking, but it's a shaking that's moving, a shaking that carries energy from one place to the other. This, by the way, is a nice demonstration of water waves. Water waves, as I said, travel on the surface of the ocean, but not completely on the surface. After all, the water is moving up and down. The water underneath must be moving up and down, too. The way it works here, the water actually moves in circles. This is the surface of the water, this wire here. So if you look at the way it moves, this is how it goes. And you can see the wave is moving from the left to the right. But each little bit of water is just moving in a circle. This is not a very smooth circle. Oh, this is what happened here. This bit of water, there we go. Okay. Underneath, the water moves less. Interesting fact about the water waves. Those of you who are swimmers, this is a useful fact. Well, using up blackboards. No? Come over here. Haha. Okay, here's the surface water. The water is actually moving in a circle. When the water here is at the top, and when you go swimming, I hope some of you have done this already, you go out there and you feel yourself moving in this circle as the wave goes by. Over here it'll be at the bottom, and then the surface of the water will look like this. As the wave moves by, this one is coming up and then going forward and then going down, moving in a circle. If you go under the wave, under the water, it's also moving in a circle, but a smaller circle. And then a smaller circle. So when a wave is coming by, if you don't want to be affected by the wave, you dive under the wave. And here's a nice rule of thumb. If you want to know at what point does this get small, it gets to about 1/3 of the value. 1/3 of the value when you get down to a distance which is equal to the wavelength divided by 2 pi. At this distance, the wavelength divided by 6, about 2 pi, you get down that far. If you see these waves, and they're 10 feet apart, so let's say they're 12 feet apart, get 2 feet down, and the motion is reduced by about 1/3. The actual number is 2.718. It's a famous number in calculus called E. But it goes down by about a factor of 1/3. So the water moves in this sort of a pattern. Music, as I said, let's see if this thing is still, if I can get this back now. Let me show you a nice aspect of this synthesizer. You look at the lower plot, and you see these nice sine waves. Let me put this on whistle. And you see how regular that is. The upper one shows the frequency. Suppose I'm changing the frequency. Play chord. I'm not a very good composer. In the lower one, you see all the different frequencies together. Let me change the plot now to something that records the history of the frequency. So instead of it being an oscilloscope, I'm going to call it a spectrogram. Now what a spectrogram is doing is it's showing you which frequencies are present when. You notice how it's moving gradually to the left. Let's try a high frequency. You see that line? The vertical line, let me get my laser pointer here. a higher frequency. What it's recording is the fact that there was this high frequency for this period of time. Now there's just me talking. See, it's a lower frequency. Higher. Lower. Yeah! Mixture of lots of different frequencies. So this is what's called a spectrogram. Now, what a spectrogram is basically doing is doing a piano analysis. If I play two frequencies here at the same time, you see the two frequencies. A spectrogram is also what was used to analyze the voice of Osama bin Laden. As I'm talking here, hello, my name is Osama bin Laden. I wish to get rid of all the people I don't like. And I particularly hate Saudi Arabia and the United States. The pattern that you're seeing there is different for every person because you have different frequencies. It has to do with the structure of your lungs, the structure of your body. It has to do with the structure of your vocal cords. It has to do with your habits. So the spectrogram becomes the key feature. Now, you can ask, how well can someone fool something in a spectrogram? Suppose they cut and paste a little bit of Osama bin Laden's words into something else. Can you tell? Well, what you would see in the spectrogram are sudden shifts. These can be picked up very quickly. Things here are changing gradually, but if there's a sudden change, if I'm talking and suddenly I paste in a different voice altogether, if it's just cut and paste, you can see it. So in order to do a good job at fooling people, you need to do a good job at cutting and pasting. It requires a certain level of skill, which I think is within the capability of Al-Qaeda. I do believe Osama bin Laden is dead, but that doesn't mean we're not going to keep on hearing signals coming, and the voicegrams will continue to analyze that signal. Next week, we get into light waves, and all of this information on waves is going to prove important.